This is the solution to the APES FRQ 2011 number 2. Um, in these FRQs, we're just focusing on the mathematical computations. So we're going to focus on part C of this problem. If you're interested in looking at the environmental science questions that are related to a problem like this, all you have to do is Google APES FRQ 2011. Typically, when you Google that, the first thing that comes up is the scoring guide, but then the second thing that will come up is the actual questions. So you can take a look at both of those to see what questions are being asked in relation to this environmentally and what are the answers. Here we have coral reefs are produced when corals acquire calcium ions and carbonate ions from seawater and deposit solid CaCO3 to form their exoskeletons. Scientists are concerned that relatively rapid decreases in ocean water pH will hinder the deposition of CaCO3. The graph below, shows the amount of CO2 dissolved in ocean water and ocean water pH, shown in parentheses, since 1850 and the predicted changes through 2100. So you can see historic levels are in gray and predicted levels are in black. And so if we're looking at the graph, part C doesn't have much to do with this. You can, again, Google and see what kind of questions they would ask about the graph. But things that you always want to keep in mind are, typically time is always the x-axis, that horizontal axis, because it's always independent. That's the independent axis, and time just marches on no matter what we do. So it's starting at 1850. That would be considered zero time, right? This is when data was first started being collected. And then you can see that they've spaced their increments by every 50 years. And then if we look at the y-axis, we see the dissolved carbon dioxide and how they're measuring it. And so everywhere along this curve, you can see these ordered pairs. So if we're looking at 2000, what would we see the dissolved carbon dioxide being? And so if we pinpoint right there, right, we're a little less than 550. And so remember, ordered pairs in math are just ordered pairs on graphs. There's two data points, your x value and your y value. So the year 2000, how much dissolved carbon dioxide? So again, let's go ahead and start focusing on C. So it says, in order to model the effects of ocean acidification on coral reefs, some simplifying assumptions can be made. Using the assumptions in the table below to perform the calculations that follow. So the three things that we have in this table are: assume that the total global area of corals grow in reefs is 2.5 times 10 to the 11th meters squared. Assume that corals grow only vertically and that the average vertical growth rate of corals is 3 millimeters per year. And last, assume that the average density of CaCO3 in corals is 2 times 10 to the third power kilograms per cubic meters. And this is why we're focusing on this particular problem where we are right now in our math lessons, because we're talking about density. So how much mass is in each unit of volume. All right, so Part 1 of Part C. Calculate the current global increase in volume in meters cubed of CaCO3 in coral reefs. Show all of your steps in your calculation. And so even if you've been reading this and you're like, I have absolutely no clue what everything is talking about, I want you to always think back to math. And we're looking for volume. And we know that when we find volume, we're looking at the area of the base times the height. That is our general volume formula. And so when we're looking at area of the base, all right, I just highlighted three things. So there's area of the base. Now, if we look at the right that's highlighted, it says area equals square units. So when you're trying to find volume, we want to first start off with square units, right? And that first part of the table, assume that the total global area of corals growing in reefs is 2.5 times 10 to the 11th meters squared. So this not only has the word area, but it also has that square units, meters squared. And so when we're looking for volume, that is going to be our base. Next, we want to multiply by the height. And so again, highlighting height. Remember, again, if we're looking to the right, height is linear units, right? It's one-dimensional. It's like stacking the area of the base. And so when we look at that millimeters, that is a linear unit. And so when it says assume that coral grows only vertically, we can even picture vertical as a height. And so that 3 millimeters is going to be our height. And now that last part is we have this per year. Now per year means annual. And so if you look at the question, it says calculate the current annual global increase in volume. And so all of this is going to work together to what we want. So our volume is equal to the area of the base, which is 2.5 times 10 to the 11th meters squared. And then times the height, which is 3 millimeters per year. So we've got that annual aspect going on. Now, I want my volume in cubic meters, meters times meters times meters. But if I look at my current equation, I have meters times meters for the meters squared times millimeters. That's not going to get me what I want. So I need to convert the millimeters to meters. So I'm going to do that now. We know that there are 1,000 millimeters in 1 meter. We want the millimeters in the denominator so that they cancel with the millimeters in the numerator. And so I did 1 millimeter over 10 to the third millimeters. The reason I did it that way is we already have information in scientific notation. So if I were normally to have written that 1 meter over 1,000 millimeters, 1,000 has 3 zeros, so that would be 10 to the third power. Now we see millimeters in the numerator and millimeters in the denominator. Those have canceled. So now when we multiply our units, we have meters squared times meters in the numerator, which is going to be cubic meters, and year in the denominator. So we're going to multiply our numbers across the top and divide by our denominator. Remember that 2.5 times 10 to the 11th is multiplication, so that is in the numerator. So when I have 10 to the 11th in the numerator and 10 to the third in the denominator, I take the exponents and I subtract. So we're going to have our digits. 2.5 times 3 is 7.5, and then 10 to the 11th divided by 10 to the third is going to be 10 to the 8th. Meters squared times meters is meters cubed, and this is all happening per year. So did we answer our question? We found annual per year, global increase in volume, cubic meters. Moving on to part 2, we want to calculate the current annual global increase in mass in kilograms of CaCO3 in coral reefs. Show all steps in your calculation. And so what we want to focus on is what are we given, right? What information are we given in the question, right? We're given that we're looking for mass in kilograms. And so when I look at the 3 parts of the table, I want to focus on the thing that has that unit, and it's the density, right? Assume the average density of CaCO3 in corals is 2 times 10 to the third kilograms per cubic meter. Now, I don't want density as my answer. I want mass by itself. And so what I have to do is I have to get rid of that volume aspect of it. So I'm going to start with the density, 2 times 10 to the third kilograms over cubic meters. Now, if I think about dimensional analysis and all the work that we've done throughout the year, if I want kilograms by itself, I want to cancel cubic meters. So since cubic meters are on the bottom, the denominator, we want to multiply by a value where they're in the numerator. And lucky for us, in part 1, we found volume, cubic meters. So we're going to multiply by our answer in part 1. So we're going to multiply by 7.5 times 10 to the 8th cubic meters. And when we do that, we see that the cubic meters in the denominator cancel with the cubic meters in the numerator. So multiplying across, we have our digits. 2 times 7.5 is equal to 15. And then our exponents, 10 to the 3rd times 10 to the 8th. Since they're being multiplied, we add our exponents, which gets us 10 to the 11th. The unit of measure in the numerator is kilograms. The unit of measure in the denominator is years, which again, we are looking for annual global increase. So annual is per year, so that's all good to go. The only issue I have now is that we're not in scientific notation. So remember that in scientific notation, we want our digit part to be between 1 and 10. And so that 15 exceeds it. So we need to move our decimal place over to the left 1. To balance that, we would increase our exponent by 1. And so we would get 1.5 times 10 to the 12th kilograms per year. On to part 3. Because of ocean acidification, it is expected that in 2050, the massive CaCO3 deposited annually in coral reefs will be 20% less than is deposited currently. Calculate how much less CaCO3 in kilograms is expected to be deposited in 2050 than would be deposited if ocean water pH were to remain at its current level. And so here, again, we're focusing on kilograms. And so if we want kilograms, we really want to think about what we just did in part 2. In part 2, we calculated the current mass. So if we want to predict what's happening in 2015, we want to use this information that's being provided. It says 20% less. So we want to find 20% of what we calculated for the current mass. And so remember that 20% as a decimal, we would divide by 100, which would get us 0.2. But when we work within scientific notation, I can move my decimal point one place to the left. So I would subtract 1 from my exponent, so we would have 2 times 10 to the negative 1. So all I'm going to do is take the current mass that we calculated in part 2 and multiply by 2 times 10 to the negative 1. And so multiplying across the top, we have 1.5 times 2 is equal to 3. And then 10 to the 12th power times 10 to the negative 1, we add our exponents. 12 minus 1 is 11. And our units stay the same. So we have 3 times 10 to the 11th kilograms per year.